Hello everybody, welcome back to this training on natural language processing, and this is going to be a hands-on session in R where we will implement some of the concepts that we went through in the previous session. So just a quick recap. In the previous session we went through how we can organize text data in a structured format, and we defined something what we call as a document term matrix or a document feature matrix, right? And then we also concluded that even though this kind of a representation gives us a structured representation of the text data, but there are some challenges that we run into, specifically the challenge of dimensionality as well as the challenge of sparsity. So this is how the representation of the document term matrix would look like. There would be the documents or the observations would be arranged in rows, whereas the different tokens and the words will be arranged in columns. So in this case we are assuming that there are k unique words in the entire data set of text, and we also discussed that typically the number of unique words in the text will be quite huge, so k here will also be quite large, which means that this will be a matrix with an enormous number of columns. So with that we will move to the hands-on part of the training. So let's set up the environment for that. So I have opened up R out here. So okay, let me do a little bit of cleaning at the onset. Let me clean up the session a little bit. Yeah, I'm done with that. Okay, so I'm using RStudio GUI here for the purpose of the hands-on, and I'm using a 3.4 version. I don't remember exactly which version it is. It's sorry, not 3.4. I'm using 3.5.1 version, but then anything 3.4 or higher should be good enough for whatever that we will do in terms of hands-on in this training. So so this is how we are setting up our session, and in terms of the packages, as of now, as you can see, we are using 3 packages out here, which are quantdata, read text, and dplyr. Dplyr we will not be using in this hands-on, but subsequently in some of the hands-on we will be using it, and quantdata and read text we will be using. So quantdata is the core R package out here that we will be using. So it's a text handling package of R. It's quite efficient, it's quite useful, and most importantly, it has got very good documentation. So if you search for quantdata documentation in browser, I think within the first 3 search results you will get very detailed documentation of quantdata. Some people also use the TM package in R, the text mining package, for doing a similar kind of task, but I personally tend to prefer quantdata over TM, so I'll be using quantdata for the purpose of this training. Okay, and in terms of the data that we will be using for some of the illustrations, as I was alluding to in the previous video, that we will be using a data set of product reviews from Amazon. So there will be 1,000 product reviews, and each review will either be a positive or a negative review, and we will have a field which will denote the sentiment, whether it's a positive review or a negative review. So this is how the data set will look like. So these are the reviews which are in the first column, and the second column it denotes the positivity or the negativity, the sentiment polarity of the review, and we have 1,000 such reviews from Amazon. Okay, so all set. So what we will first do is, first things first, we'll try and read the data. So the read text package actually helps us read the data, and we'll also save the data in the form of our data frame. So we are done with that. So we have read the data, and as you see, there are 1,000 observations, 1,000 reviews which has been read. Now I'll quickly open this up and see. So if you recall, the data set in CSV file that I was showing you, it had just two columns, review and sentiment. But then when I come back to the data set that has been read in R, Quanteda has actually created a column for me which is called doc id. It is basically some kind of a key or a unique identifier of every individual review. So that's quite nice of Quanteda. It creates it on its own, and it's very helpful in indexing reviews at a later stage as well. Okay. And just to be sure that we have read things correctly, we'll check. Yes, there are 500 positive reviews and 500 negative reviews. So sentiment is the field in the dataset which captures the polarity of the reviews. Okay, we'll do something now. So we will try and calculate the length of each of the reviews, right? And then see that how does the length looks like. So let's go ahead and do that. By the way, if you feel that I'm rushing through this course without actually explaining some of the syntax here, you're right. I'm doing it purposefully because the objective here is, not to explain the R syntax, but is more to sort of illustrate some of the concepts. These codes anyway will be available as a part of the training. So I'll upload them separately in a GitHub repository, so they will be available for later reference as well. Okay, so let's go ahead and run this. Okay, we have run this part now. So I'm assuming that all of you are familiar with ggplot2. It's one of the most popular R libraries for getting some fancy charts. So we will use that, and we'll try and get a chart and then interpret the results. We have some nice intuitive results out here. So this is the chart that we have got. Let me zoom it out. Yeah. So what we see here is that this is a distribution of the length of the reviews, and I think we briefly looked at it in the previous video as well. So what we see is that for the positive reviews, the length is quite small compared to the negative reviews. So whenever people have bad things to say, they generally say much more than when they have good things to say. Common human psychology. And this is very interesting insight, very useful insight, when it comes to analyzing text data. And what is even more interesting and even more intriguing is that thus far, apart from importing the data set, I haven't done any NLP as such. So I've just counted the length of each of the reviews and then looked at the distribution. So that itself is giving some great insight. So even if you are, just a tip out here that even if you are handling text data, try and do the trivial things as well. At times, even the trivial things give good insights without going into the more fancy steps of NLP. Okay, so we'll now go a little bit into the fancy things. So this is important. So what we will create here is something which is called a corpus. Now corpus is nothing but it's a collection of all the text together. So that's what it's called as corpus in the context of natural language processing. And we are creating a corpus out here, and the name of the collection is we are naming it as full text. Okay. And we will now go ahead and create the document term matrix. So DFM is the function to do that, and it is being applied on the corpus variable full text. And we are doing something very basic. We are removing the punctuations from the sentences. Okay, and the DFM is a function which comes as a part of the Quanteda package. Great. So let me run this part. Okay, I have created the document term matrix, and if I sort of convert it to a matrix format from a Quanteda format, and then see the dimensions, I'll see that the dimension is 1000 cross 1890. So as we were seeing previously, that in the document term matrix, the number of rows is equal to the size of the data set that we have out here. So in this case we have 1000 reviews, so there are 1000 rows, and 1890 is the number of columns, which is equivalent to the number of unique words or unique tokens that we have in all of these reviews. So just think of it, these are just 1000 reviews, and they have led to almost twice the number of unique words. So that leads to the dimensionality problem, right? Okay, so we discussed some of the ways to do away with the dimensionality problem, right? So we said that we will remove some of the stop words, we will remove some of the numeric stuffs present in the text data, so on and so forth. So I'll move on to the next code and show you, how we can implement those dimension reduction approaches in R using the quant data package. So all that I'm doing here is, I was creating the document term matrix using the DFM function, and I'll do the same thing, but I'll pass on some additional options here. So I will say that to lower equal to true, which means that if the same word appears in uppercase and lowercase, they will be converted. The uppercase will be converted to lowercase, and it will be treated as one single word. I'll do stemming. If you recall, stemming was basically if I have a parent word and then I have a suffix added to the parent word to get another word. For example, talk, talking, bringing. So in all these cases, the suffix will be stripped off and it will be converted to the parent word, so that once again what we will have is, if we are saying talk and talking, they won't be treated as two different words. Talking will be converted to talk and it will be treated as one single word, so it reduces the dimension. We will remove the punctuations and we will of course remove the stop words. If you recall, we said that we will generally tend to work with the nouns, verbs and the adjectives. Everything else that is present in the sentence is more for grammatical construct and aesthetics of the sentence, and doesn't add incremental context. So as far as analysis of a sentence is concerned, we can safely strip them off. So we'll quickly run this, and we have created this DTM, and we will see what is the dimension of this. So if you see, as intuitive, the number of rows remain the same because we are not doing any sampling out here. However, the number of columns, which is basically nothing but the number of unique words or number of unique tokens in the entire data, that gets significantly reduced. In fact, that gets reduced by almost 25%. So earlier we had some 1900 columns. Now it has gone down to 1400, which is a significant reduction, and we have achieved that by doing these steps. So we are removing the stop words. This is the single most important contributor actually, by removing the stop words and then doing some amount of stemming, and also treating lowercase and uppercase as the same thing and not different things. Okay, great. So having removed the stop words and reduce the dimension of the document feature matrix, we'll now try and see that in a given review, what is the average number of words that we are left with after we have done this reduction in dimension. So we'll do some basic operation here. So what we will do is, okay, let me open one of the document term matrix maybe. Or I can actually go back to the illustration here. That will be quicker. So if you see in the document term matrix, if you add along the rows, all that you get is in each of the documents number of terms that are present, right? Because let's say in document 1, T1 will be number of times the word T1 is present in document 1. Similarly, T2 will be number of times the word T2 is present in document 1, so on and so forth. So if you add along the rows of the document term matrix, what you will get is the number of words which are present in each of the documents. So that is exactly what we will do. So we will basically add the rows of the document term matrix, and then that will give us the number of words in each of the documents, and we'll plot that in the form of a histogram using ggplot. Yeah, this is how it looks like. Not the most attractive color, but serves the purpose. So what we see here is that we have a token count per document in the x-axis. So we see the mode is around 5, right? So most of the reviews have around, on an average, have around 5 or 6 words in them, and that might sound quite weird, because how can you write a review in just 5 or 6 words? But then remember that we have done some dimension reduction here. So we have removed the stop words, we have removed we have removed the punctuations, and we have also converted lowercase and uppercase into one single format. We have done stemming. So everything taken together, we have achieved some dimension reduction. So that has rendered a scenario where we see that typically every review have around 5 to 6 words, and that is good enough to get the context of the review, because we are not interested in the grammatical construct or the aesthetics part here. But what is equally interesting here to look at is that even though we are saying that every review have around 5 or 6 words in it, but if I look at the total number of unique words that we are left with, and we are talking about 1,000 reviews here, right? So total number of unique words that we are left with is something that we checked in the dimension. So we have, even though there are just 5 or 6 words in most of the reviews, but then if we look at the unique words across all reviews, that is still quite large, 1425, right? So we have reduced the dimension, but it's still not small enough. The other thing that we want to check is something that we called as sparsity. So as I was referring to in the first video as well, that the document term matrix will have a lot of zeros, right? Because not every word will be present in every observation. So there will be a lot of zeros in the document term matrix. In fact, it has an incredibly high number of zeros. So if we calculate the sparsity of the document term matrix here, we will see, and the sparsity basically means that what is the proportion of observations in the matrix out of all observations which are 0. So we'll quickly try and calculate sparsity of the document term matrix, which is DTM in this case, and you see the sparsity is 99.6%. So 99.6% of the elements in the matrix are 0, and obviously the remaining 0.4% have values. So if I try and open this, I'll try to do this at the cost of wasting some time, because it might take some time to view this, but let me see how much time it takes. Okay, so it's too large to view, looks like. Let me view the matrix version then. Yeah, that's better. So it's not fully opened up. will take some time to open up. So the reason I'm opening the document term matrix is to give you a visual illustration of this sparsity thing that I was referring to. So when I say that 99.6% of the elements in the matrix are 0, it might appear to be an overwhelming number, but if you actually look at this, then you will understand that how that scenario is actually taking place. So if you look at the first review, so these columns are basically the number of unique words which are present in all of these 1000 reviews, right, taken together. And how many columns do we have? We have some 1490 columns, right? We looked at the dimension of the matrix. So let's look at this word convert, right? It is present in the first review, but it's not present in the second review, third review, so on and so forth. So one word, or rather, if we look at one review, it is not likely to have a lot of words, right? It will have only a few of these words amongst this total collection of words. And we have already seen, if you look at this graph also, we have already seen that typically in a review we have around 5 to 6 or 7 words max. So, and in total we have close to 1500 words, right? So obviously if we have a total of 1500 words, unique words, and a given review can have around 5, 6 or 7 words, we will have a lot of zeros in these rows, and that is what leads to this sparsity of the document term matrix. In this case it is 99.6% sparse. Okay, I hope that was worth it, because it took some time opening the document term matrix. Let me close it now. Okay, now having represented the text data in the form of a document term matrix in a and getting a matrix which is sparse, and its dimension have been reduced, but it's still on the higher side. So can we do let's say some of the traditional supervised learning that we typically do with numeric or categorical data? Okay, so let's look at this illustration first. So this is a generalized linear model, an example, or let's say, to keep things simple, logistic regression, which is a particular case of generalized linear model. So when we run a logistic regression, we typically have a matrix, which has all the x variables, the feature values, and we have a y, right, which is the label or the target. In the context of text data, as we have also discussed previously, if we assume that the document feature matrix or the document term matrix is analogous to the data matrix or the design matrix that we get in case of numeric or categorical data, and y is some label. Let's say in case of the example that we are looking at, it can be the sentiment polarity of the reviews as well. So if we have a setup like this, can we go ahead and build logistic regression in a setup like this? So let's look at this aspect. So the logistic regression model, or for that matter, if I call it a linear regression model, so the equation is of the form y equals x beta plus epsilon, right, where x is the document feature matrix in this case, beta is the parameter to be estimated, and epsilon is obviously the error. And if we do a generalized linear model, then instead of having y here, we will have some function of y here, right? Okay, so from this equation, what it turns out to be, the parameters or the betas are estimated using this expression. So I'm skipping some matrix algebra here, but it's sufficient to know at this time state that the parameters are estimated using this expression. And there is a particular reason why I have underlined, and I put a double underline under this part. So there's an inverse of a certain matrix, which is being calculated in order to arrive at this parameter estimate. And the matrix of which the inverse is calculated is basically the product of two matrices, the transpose of the document feature matrix times the document feature matrix. So we are doing this matrix product and then calculating the inverse. So this is involved. This is the quantity involved in calculation of the parameters. Now let's see how does this quantity looks like for the document feature matrix that we have with us, right? So we'll try and transpose the document feature matrix, do this matrix multiplication, and then try and calculate the rank. It's not that difficult. Okay, let me try and let me not clutter up this code and create a new code. Okay, so we have a document term matrix which is dtm.m, and I'll create the transpose of that. So let's say I'll do this is the transpose of dtm.m. Okay, so t is the function which gives the transpose, as simple as that. And we will calculate the product matrix here. We'll do a matrix multiplication of the transpose and the DTM. So we'll do t underscore dtm.m star dtm.m. Now, just a word of caution here, guys. If you do this, it doesn't actually do the matrix multiplication. So it will basically multiply the individual elements of two matrices, which is not what matrix multiplication is meant to be. So you have to write it in this way, and then it will do the matrix multiplication. So let me run the first part. It is done. Let me run the second part. It is done as well. And then I'll try to find the rank of this product matrix using the function QR. QR is basically a function which does the QR decomposition or the QR factorization of matrices. So we'll do that. We'll do QR of this product matrix. Okay, and then I need the rank of that. So I'll run this. It will take some time to calculate the rank. Okay, so here we see the rank is 860. Now, which means that this matrix, this product matrix, so what is the dimension of this product matrix, right? So the dimension of and then we can actually work out what is the dimension of the product matrix. Instead of try and speculate, we will work out the dimension of the product matrix. Yeah, here you go. So it's a 1425 by 1425 matrix, right? And so the order of this product matrix is equal to the number of columns that we had in the document term matrix, or in other words, the number of unique words or unique tokens that we had. However, when we calculate the rank comes out to be 860, which means that this matrix, this is not a full rank matrix, and hence from the context of as far as the context of matrix algebra is concerned, we cannot calculate the inverse of this matrix, which means that this equation goes for a toss. It is not so easy to get the parameter estimate using this equation, because we cannot calculate the inverse out here because this product matrix is not a full rank matrix. And